All right, continuing on with some statistics things. After we have some data, then we have to decide, is there a mathematical equation I can attach to this data that lets me make predictions? Okay, and that's kind of the goal with statistics. Can I predict what's going to happen next? Can I say within my data, was it a successful experiment? Was it a successful trial? Did we make the right decision? Did we do the right thing? Okay, and a lot of that comes down to, can you apply a mathematical model, and will that and then, once I have a model, the college algebra portion of it is, okay, I have this model, I kind of understand how that works, I know the shape, I know what kind of numbers should go in and out of it, and that will help you, those two pieces of information combined, help you kind of make a decision. Is it going to keep going up? Is it going to lay back down? Is it going to start declining rapidly? Is it going to decline slowly? Okay, all of that kind of information comes from these two branches of mathematics kind of working together. Okay, now when we do this section, you are going to be extremely, extremely tempted to just watch this and say, oh yeah, I know how to do that. Please, 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 take the time, go out of the video, type all of this into Desmos, make sure that you can make Desmos work, because that will help you when it's time to do the homework. Okay? Math is not a spectator sport. You have to sit and practice and try. Okay? All right. 4.3 is going to start with what we hope is the most basic, simple, easiest parts of these types of models. We're going to start with linear. Okay, a straight line would be ideal. If everything would go in a straight line, everything would stay incredibly organized, the world would move smoothly, everything would be wonderful. However, we know that's not how this works. But for now, 4.3, we're just going to talk about linear lines. Okay? All right, this is real data from a real scientific experiment. I don't have it at my fingertips to give it credit, but it is credited in the textbook. Okay, you have number of cricket chirps in 15 seconds at several different air temperatures, and this is in America, so it is in degrees Fahrenheit. Okay, so does there appear to be a trend in the data? And just kind of look at it. Okay, I've got a scatter plot, got a bunch of data points. Kind of looks like maybe if I were to take a line and put it right about there somewhere, a little higher, a little lower. This is obviously just a sketch. But the points kind of stay around that line. They stay pretty close to it. Okay, and that is what we mean by, is there a trend? And if I can see a trend, right, if I can see a pattern, then I can apply math to it. Math is just analyzing patterns over and over and over and over again. So if I can see a trend, then I'm allowed to use math. Okay. Now, when we analyze this data, we are eventually going to start to make predictions about the data pieces that we've collected. And there's two ways to make predictions. One of them is inside of our data. Okay, so this is exactly the same graph. So inside of my data, between the points, is called interpolation, and we think of this as inside our data. Okay, this means our model is strong. It's supported by a lot of pieces of data. We have a good idea of what's happening. It's good. Okay, if I start analyzing outside of my data, so over here to the right, out here to the left, when I'm past my last scatter plot point, that is called extrapolation. Okay, and this is outside of our data. And what happens is that we get something called model breakdown, and I don't remember if that's hyphenated or not, so my English majors, just pretend you saw nothing and move on. What that means is, okay, this is at 50 degrees, or sorry, this is at 80 degrees, okay? Let's say I make 2 more steps and I am now in southern Arizona and it's 100 degrees. Do I really think the crickets are going to chirp at 70, 80 chirps per minute? I don't know. Okay? I don't have good data for that. I'm from Arizona. I can tell you at about 100 degrees, almost nothing is out in the open. Humans aren't, crickets aren't. It's too hot. It's just plain old too hot. So is this model going to continue? I don't know. I just plain old don't know. Okay? And you can do the same thing in reverse order. Do crickets, according to this model, if it hits 30 degrees Fahrenheit, crickets stop chirping? Is that true? I don't know. Maybe in some parts of the country, not in others. We don't know. Okay, and so when we talk about model breakdown, that's what we're really saying, is that I just don't have enough data in those places to be able to confidently say, this is how it's going to go. Okay, so model breakdown just means, plain and simple, there's too many factors for me to make a confident decision about what's going to happen. Okay. All right. And then as we start to make these mathematical models, as we start to put a mathematical function over our data, we need to know if that function is good. Okay. Is it good? Well, what we do for that is that we assign a number. And I could show you how this number is calculated, but I actually think that your stats teacher is going to go over that, and they have more time for it than we do. So I'm going to let them explain it. But we take some measurements, we take some calculations from variance, how far things are away from that line where we've decided has a trend, and they kind of minimize those distances. Okay, we're not going to calculate it by hand. We are going to let technology calculate it for us. And what this does, an R value of 1 or -1, okay, this means I have really, really good models. Okay, my mathematical function hits every single spot on that scatter plot. Every single one of them is right on the line. Okay, as my data gets, or as that R value gets closer and closer and closer to 1 or to 0, that means I have a terrible model. And actually, probably that I shouldn't even be using a model. Okay, meaning that there is absolutely no pattern at all to our data. Okay, so a -1, we'll come up here to this kind of idea. A -1 means that all my data points are on the line. It just so happens that that line is going down. So I'm trending downward, but it's a really good model. It's just a model that goes down. Okay. An R value of +1, which is over here on the left, would mean I have a really, really good data set. I have an excellent model. It hits every point on my scatter plot, and I'm trending upwards. I'm moving up. I'm getting more on all of them. Okay? And R of 0 here means that I am just not really that good, right? There's no pattern there. I could put any line anywhere and it's probably going to work. And so we just kind of say, that's a 0. There's no correlation. There's no pattern here. I don't really know what's going on. Okay. Now, there are different ways to be 1s and -1s. So that information takes care of that top row. This is not a great graphic, but we're going to do the best we can. Okay. A +1, all 3 of these are examples of +1s. A +1 just means all the data is on the graph, or all the data is right on that line, and it happens to be moving upward. It doesn't tell us how fast it's moving upward, just that it has a general upward motion. Okay? Now with -1, same idea. All of the data points are on that mathematical line, and it just so happens that it's going down. I don't know how fast it's going down. I don't know if it's drastic or gradual. I just know it's moving downward. Okay? Now, this last line here brings up a really important idea. Okay? Nonlinear patterns. And nonlinear patterns means that R value does not exist. Okay? And R value only applies if you are using a straight line. Now, there is a similar measurement that we use for nonlinears. It is not an R value. Okay? And when we are working in a nonlinear fashion, we tend to use a different calculation. And we'll talk about that in 6.8 very briefly. But an R value is only for straight lines. Okay? Sorry. All right. So pause it, put some R values on this, give it a chance, see if you can decide, and 100% be nice to yourself if your numbers don't match what I'm about to write down. It's an estimation, meaning we're just making a guess. Okay? So take these three, make a guess, and then I'm going to write down what I would guess. And as long as you're kind of in the neighborhood, we're okay. You're probably okay. All right? All right, this first one, the points are all over the place. If my trend line, the goal of my trend line is to have half of my data points above the line, half of them below the line, and I'm sort of tracing out a pattern that it follows, I don't see one, okay? So I would say your R value is probably pretty close to 0. Now, could there be an R value? Sure, could be like a 0.1, a 0.2. It's going to be really, really low, but it's probably pretty close to 0. Okay, closer to 0 than it is to 1, for sure. Okay, now the next one. These ones do actually have a pretty obvious trend, right? It's going down as it goes from left to right. So my R value is going to be negative because I'm moving in a downward trend. And because it's also kind of going downward, it's not a 1, okay? All of those data points aren't really, I mean, they're around the line, but they're not all exactly on that line. So it's not a 1. So I would say maybe like a 0.8, 0.7, 0.8, maybe even like a 0.85. Okay? You're just off the line, but closer to 1 than you are to 0 for sure. Okay? Now this next one, I would say a similar value, but now we're moving upwards. These look a little bit tighter to me, so I'm going to say this is like a 0.9, 0.85, 0.9. Okay, we're just getting a little bit closer to being exactly right on those lines where we want it to be, right? A perfect mathematical model goes through every point. So the closer I can get to those lines, the better my model is, the more I can rely on it. All right, now this is the part where you are going to want to open Desmos. You can use the app, you can use the website, it doesn't really matter to me. Just make sure that you are able to use Desmos, okay? Now to do a regression means I'm going to take a bunch of points, so meaning I'm going to make a scatter plot, and then I'm going to have the computer, I'm going to have Desmos do the work and give me a mathematical model. Then once I have that model, I can use that model to create or make predictions, right? I can use that model to do all of the things that I want to do with that data. So open your Desmos. Up in the top, you can either literally just write the word table, just type in table right there and a table will appear, or you can hit this plus sign up here and then choose table. Both of them will result in something like this. It's going to pop x1, y1 at the top, and then it's going to give you an empty row. And then you can fill in that data. Now, what I usually do is I type in my x values all the way down. And if you just type in, like I would type in 1994, hit enter, it'll add a row. Hit enter, like 1995, hit enter, it'll add the next row. Okay, so just type in your rows, or type in your data, it will fill in the rows. And then I like to go back and fill in my y values. You can do it whichever way, whatever floats your boat, whichever method you prefer. It doesn't matter. As long as all of the data gets in there, we are good. Okay? Now, the next thing you want to do is be able to see your data. You want to be able to look at that scatter plot. And so right here in the bottom left corner, you're going to see a little magnifying glass with a plus sign. If you will touch that, that's a button, okay? If you will touch that, then over here where the graph is, it's going to adjust your zoom automatically so that you can see all of those points. Okay, it's going to zoom into that scatter plot so that you can see what's going to happen. Okay, for a linear regression, okay, y1 is approximately mx1 plus b. Now there's a couple of things that you need to check to make sure that you're doing this right, or you're not going to get a line drawn. Okay. First of all, we're working with a straight line. Hopefully you remember by now that a straight line is y equals mx plus b. So whatever model I think I'm going to fit, I'm going to go back. I'm going to grab that toolkit function that we've been talking about all semester. I'm going to grab that toolkit function and I'm going to apply that model. I'm just going to write the toolkit function. Now there's a couple of things that are important. There is, at the top of your table, this says x1 and y1. If you do a bunch of these back to back to back to back, eventually you're going to accidentally run across a scenario where one of those tables is going to say x2 and y2. If that changes, okay, you can either change this to say y2 is approximately mx2 plus b, or you can tap into these boxes and change them back to x1 and y1. Okay, the variables that you use here have to match the variables that you put in that model. If they don't match, you're going to either get an error or you're going to get a line that doesn't match. It's going to be like a straight horizontal line and it's going to look weird and it's not going to give you the information that you want. Okay, so make sure that those match. After typing in that spot, you're going to get something. Well, let's back up a step. Okay, so after just creating the table, okay, so over here, I've got my table. I've put in my data points. I hit that little plus sign. Notice that it's gone now because I've zoomed, it's done its job, and so it's going to kind of disappear until I make a new table or do something to that table, okay? It has zoomed in to where it thinks I need to be to see that data. Right? Now I can see there's a trend. It's generally moving upwards. It's pretty close to my line, right? It's pretty close. I've got x1 and y1 here. So our next step is going to be to type y1 down in this second box is approximately, now that's a tilde, it's going to be up, if you're using your iPad, it's the button on the very top left of your keyboard. You'll have to hit shift and then that button and you'll get the tilde. You can also use the keyboard that's built into Desmos. It will have it on there as well. Okay, so m x1 plus b. After you do that, it's going to show up like this. Okay, it's going to draw this nice line. The colors may change. The colors might be different every time. It doesn't matter. Okay, you're going to get this line drawn. And then it's going to give you some information. Okay, now the mathematical formula for this set of data, you're going to take your m value from down here 2.20909 times x plus, well, I guess in this case minus, your b value, so minus 4291.61. Okay, that is your model. The computer did all the work. You put in the data points, you gave the computer a command, it gave you this as an answer. That's all my work. That's all you need to do. Okay, this is why you don't have to turn in scratch work for this section, because the Desmos is going to do it all for you. Okay, now how confident am I? Well, my R value is really close, like really, really close to 1. So we are very confident that our model is a good one, right? Whatever numbers we get out of analyzing this, it was a good model. R is 9965, 0.9965. And it's not actually a percentage, but it does help when you're first learning about R values to kind of think of it as a percentage. Like, I'm 99% positive that this is correct. And that's a pretty good, that's pretty confident, right? If you're 99% sure something's going to happen, you're pretty confident, right? If this was a 0, where R is 0, I have 0 confidence in this, okay? It's not a percentage, but as you're starting to kind of get used to the idea of an R value, it is helpful to think of it that way. It is helpful to think, I'm 99% confident in this. That's a good model, okay? Now, once you get your data, okay, this is a separate equation, but I'm going to show you how to use Desmos to work it anyway, okay? So I've got this regression. It spit out this block of information down here, okay? That means my model is going to be y equals negative 1.341x plus 32.234. And you can take that model, you can put it right into your Desmos, okay? I put it in the top line. Put it right into your Desmos. It's going to draw this black line over here. And it's black just because that's the color that my Desmos was on at the time. Okay. Now, use this to predict the number of sit-ups a person who watches 11 hours of TV can do. Well, I need to know, is the 11 an X value or is the 11 a Y value? So we go back up here, hours of TV watched per day, X. So it's telling me right there in that word problem, X is hours. So I want to know person who does 11 hours. So just in the next line, I'm just going to put X equals 11. And what Desmos is doing in the really fancy mathematical way is where those two lines cross, this is where our answer lies. Now you can plug in 11 and you can do the math by hand and it will give you the same answer. Or you can use Desmos. You can understand what the models are doing and how the models interact with each other and let the computer do the work. Okay, so at 11 hours of TV, this person can do, or we estimate, this person can do about 17 and a half sit-ups. Is that great? Probably not, but probably also relatively accurate, right? If you were sitting in front of a TV for 11 hours a day, you're probably not doing a lot of exercise. Okay, we're assuming this is just like literally sitting. You're not like doing something while you're watching TV. You're just actually watching TV and doing nothing else for 11 hours. Okay, seems reasonable. Can we be confident? Well, our R value is 0.896. Again, it's not a percentage, but you can think about it like it's a percentage. So if I was 89.6% confident in something, that's pretty confident, right? We would say, yeah, we're pretty relatively confident. And we're that we're that confident because our R value is pretty close to 1. Now in this case it's -1, but that's fine. Okay, it just means the correlation goes down, the trend moves in a downward direction, but it's close to a 1. And so we're pretty confident. We're relatively confident. Okay. All right, one last example of linear. I've got a setup. Okay, I've got population in the X values, I've got year in the Y values. So I'm going to go over here. I'm going to create a table, right? These are all just the points they gave me, but I put them into a table. I hit my little hourglass or magnifying glass. Now I've got a scatter plot. I did the draw me a line thing. Okay, did my regression. So all my data is down here. Now look really closely at this R value. I would say this is like literally probably as close to a 1 as we actually get in the mathematical real world. Okay, perfect ones are extremely rare. This is just about as good as it's going to get. Awesome, I got a great model. Okay, so I need to determine a function. That is what this model is. Okay, function is just another name for model. So my function is going to be, sorry, I got to zoom in so I can see it. Y is 0.005, nope, 006, that's a 5/8, times x plus 1985.41. Okay, cool, I've got my model. Okay, predict when the population will hit 8,000. So go back again. Is population an X value or a Y value? In this case, the way this is set up, population is in the X position. So I'm going to say X equals 8,000, and then come over here and look for where they intersect. This is the population. This is a year. So in the year 2032, my population is going to hit that 8,000 mark. And they don't ask for a month or anything, but if they did, it's about a third of the way through the year, and the year is 12 months, so the fourth month would be April. So I would say somewhere in April, probably near the end of April, but somewhere in April of 2032, that's when the population is going to hit that 8,000 mark. Okay, now be careful here. Even though we have a great model, this is extrapolation. And it's extrapolation by a long margin. It's not like I'm estimating right over here, right? I'm extrapolating way out. So even though I can be pretty confident in it, I'm not 100% confident because there's a lot of factors. There's a lot of things that could change, right? So we're making a good guess based on a good model, but it's not a guarantee. Okay, now that is linear regression. When we talk in 6.8, we're going to talk about some that are a little bit nonlinear. So we're going to get into those natural logs and those exponentials. Okay, this is 4.3 though. So linear, straight lines, everything should be a straight line, and you're looking for R values.